So what is bioprinting? 3D printing was founded by Charles Hugh in the early 1980s and has many applications. Within the medical field, bioprinting is considered to be the conversion of an MRI or CT scan into a 3D model by layering biomaterials onto a platform in the shape of the desired print using a computer-aided design model. The products created from the use of bioprinting are endless.
There are three main methods for printing biomaterials. The first one is laser-assisted. As shown in the diagram, a laser-assisted deposits a liquid biomaterial into a droplet to form onto an awaiting substrate. The second method is inkjet printing, which uses heat to melt ink and form droplets, which are then forced onto a substrate using a narrow nozzle. The third method is extrusion-based, which uses the motion process behind a plunger in the form of a continuous filament that is forced through a nozzle and then therefore prints onto a substrate. The factors that affect printability are cell viability, complexity, cost, and speed. These are all important to consider when deciding which type of printing method you should use, as complexity and speed can often be inverses, while maintaining cost can often always be an issue when printing something using bioinks.
Bioprinting technology is broadly used for tissue engineering, regenerative medicine, transplanting, drug screening, and cancer research. 3D printed organs on chips can match the properties of a specific disease or even an individual patient's cells, allowing researchers to easily collect reliable data for short-term and long-term studies. Another example application is the 3D printing of cardiac tissue scaffolds to replace and restore function to tissue damaged during a heart attack. Bioprinted tissues can also be used as surrogate tissue to test drugs for cardiotoxicity and personalized medicine. In cancer research, bioprinting has recently been used to investigate cancer pathology, growth, and metastasis in a physiologically relevant microenvironment.
Another application of bioprinting is modeling. Modeling is used within medical school and the surgical field. In medical school, it allows residents to look at the anatomy of a patient and also practice because the models mimic hard and soft tissue, giving them a more accurate playing field. In the surgical field, it allows surgeons to see the problem at hand from every angle so that they can better assess the situation and therefore know what they're going into before they even open the body up of the patient.
One application of 3D printing is for bone regenerative processes. So the main technique used in this is powder-based 3D printing. Bone regeneration can be aided by the creation of a porous scaffold. This porous scaffold will allow for the formation of new bone. And this scaffold will obviously be created by powder-based 3D printing. And the main needs of a scaffold are the following. First of all, the scaffold needs to be biocompatible and bioresorbable with a controllable degradation and resorption rate to match the cell tissue growth in a patient. Second, the scaffold needs to have a suitable surface chemistry for cell attachment, proliferation, and differentiation. The scaffold also needs to be three-dimensional and be highly porous with an interconnected porous network for cell growth, flow, transport of nutrients, and metabolic waste. And finally, the scaffold must have mechanical properties to match those of the tissues at the site of implantation. So we see these are all the things that powder-based 3D printing aims to achieve. However, current researchers have found some challenges when depowdering the scaffold, or depowdering is the technique where it's used the powder that is not adhered to the actual scaffold is blow dried. And since the scaffold is very fragile, blow drying can sometimes damage it, and then therefore it won't get implanted as effective into the patient. The main material that was found to be to model the characteristics of the bone was calcium phosphate bioceramics, that is, as it experienced high osteoconductive properties, and therefore this was the main area of research that it's being done in right now. And
one of the future potentials of 3D printing is organ printing. In fact, what it does is there are three main ways that this can help. There are treatment models, which can be used to identify potential success of controversial treatments. 3D printing organs can also decrease risk for organ rejection because you'll be using the patient's very own cells to create their new organs, while also reducing the need for an organ transplant demand, which can actually put a halt to drug trafficking black markets and make the demands for organs such as kidneys and livers dramatically decrease.
One direction of bioprinting is 4D printing. 4D printing adds the element of time into the mix. Currently, 3D printing takes initial state conditions and therefore nothing will change over time. 4D printing will add the time and allow the state conditions to change. It is a technology that is being experimented with but is nowhere in the final stages.